Let's start by just recalling what the definition of the trig functions are. So we have a definition of the trig functions, right? If I ask you to compute cosine of theta, what am I asking you to do? I'm asking you to draw a circle of radius 1. Start at the point 1, 0. Rotate forward by some angle theta. You'll land at some point x, y, and then what is cosine of theta given by? Vx. What's sine of theta given by? What's tangent of theta given by? And shoot, let's first sort of secant of theta. Cosecant theta. And I guess cotangent is the last one. So this is the perspective known as unit circle trigonometry. I'm going to introduce another parallel philosophy of the trig functions, which all give the same numbers, called right triangle trigonometry. And let's build that up. So here we go. So here is a circle of radius 1. So let's suppose that inside of that circle of radius 1, I rotate forward by some angle theta. So there's a leg of length 1, there's a height, there's a width. So if you look in that triangle, can you just read that? Well, let's see. So that's some point x comma y. By thinking about trig functions, can you just tell me what x is? Well, do you get that point by starting at 1, 0 and rotating forward by an angle theta? Yeah, so that x coordinate must be one of the trig functions. In fact, that x coordinate is cosine of theta. So you have this picture where x is cosine theta, y is sine theta. So now look at that picture a little bit, and let's just read some things from that picture. This is a circle of radius 1. So what's the length of the hypotenuse of that green triangle? It's 1, right? It is the radius. So look at that triangle. Look at the side length that is opposite the angle theta. What is the length of that side? It's the same as the y coordinate. So that length is y, right? Because that's what Cartesian coordinates mean. The y coordinate, if you have an xy coordinate, then you travel so far in the x direction, so far in the y direction. That's the point xy. So that vertical length is y. But on the other hand, it is sine of theta. Everyone feel pretty okay? What is the length of the side adjacent to theta? X, which is also cosine of theta. Cool. Everything, that seems pretty fine, right? I haven't done much. I've just drawn that triangle. But let's do something which may seem just random. Let's take that triangle and scale every side by a factor of 2. So double all the side lengths. So if you like, there's the old triangle, and the bigger triangle is the new triangle. What is the hypotenuse of this new triangle, which has all of the side lengths doubled? 2, because it used to be 1. It should be twice as big. What's the length of the side that is opposite theta? 2 times the original y coordinate, or maybe I'll say 2 sine theta. Because my goal is the trig functions. Calling them x and y is artificial in my mind. What's the length of the side adjacent to theta in terms of a trig function? 2 cosine theta. The answer 2y was correct, but I want to emphasize the trig functions. Now, I could have scaled this by any factor, not just 2, right? That was just like maybe a silly example. Let's scale everything by a factor of h. If you start with that triangle, I mean, I can't draw it with scale because I don't know what h is, but that's okay. If you scale every side length in that first triangle by a factor of h, then what's the length of the new hypotenuse? H. And now maybe you know why I picked the letter h. It's the same as the hypotenuse. What's the length of the side opposite theta?
H sine theta.
And now maybe just for emphasis, I'll even give that a name. That is op for opposite. Maybe I'll call this one hyp for hypotenuse. What's the length of the side adjacent to theta? H cosine theta is equal to the length of the side adjacent. And now for the payoff. You have an equation there for that you could solve for cosine of theta, right? So what is cosine of theta? It's adjacent over hypotenuse. And so maybe I'll write it first as adj over h, but maybe for extra emphasis, that's adjacent over hypotenuse. Similarly, sine will be opposite over h or opposite over hypotenuse. There's the philosophy of right triangle trigonometry. If you draw an arbitrary right triangle, and you pick one of the angles, call it theta, then the cosine of theta will always be the length of the adjacent side divided by the length of the hypotenuse. Sine theta will always be the length of the opposite side divided by the length of the hypotenuse. If you know sine and you know cosine, can you figure out what tangent is? Yeah. So let's even write that right here. If tangent is y over x, well, what is y? It's sine. So I'll get sine theta divided by cosine theta. So let's use that. Let's go over here. Tangent of theta is exactly sine theta divided by cosine theta. Do I have a formula for sine theta? Opposite. Well, you're jumping right to the very end. That's correct. But let's actually do the intermediate steps. In fact, how about, I'll do the intermediate steps. Don't change horses midstream. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Is there anything common in the numerator and denominator to cancel?
Hypotenuse.
Yeah, you can cancel the division by hypotenuse, leaving you with opposite over adjacent. Maybe an equivalent way is tangent is supposed to recover like the slope of a line. What's the slope of this red line? Well, what's the rise? It's opposite. What's the line? Adjacent. So tangent is opposite over adjacent. Those three formulas are collectively known as right triangle trigonometry. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And there are a handful of different mnemonics you can use to remember that. Maybe I'll endorse the one that well, here's the one that I'll endorse. If you want to remember, sine is opposite over hypotenuse. So, cosine is adjacent over hypotenuse, ka. Tangent is opposite over adjacent, toa. So if you can remember the syllables soka toa, then you can remember those facts. On the other hand, it didn't take us that long to build those facts, right? Maybe like 8 minutes. And I was going at a pretty relaxed pace, I think. You could probably recover those facts in much less time. So there's the thing to remember. Right triangle trigonometry tells you that trig functions tell you things about right triangles, and right triangles tell you things about trig functions. And let's see that interplay. So here's a right triangle. Maybe I'll, for emphasis, put the little boxy thing there to emphasize that that's a right angle. With one side of length 3, one side of length 4, do you think you can figure out what the length of the hypotenuse is? What factor would you use to do that? No, the Pythagorean formula, which, sorry, we kind of have two things that we call Pythagoras' law. We have the one for sine and cosine, and we have the one for right triangles. But they're kind of the same thing, right? Let's see it in play right here. So according to this, h squared should be 4 squared plus 3 squared. And we'll compute 4 squared plus 3 squared a great many times. But for now, let's just do it by hand. Eventually, you'll just remember what this is going to work out to be. What's 4 squared?
16.
What's 3 squared?
9.
What's 16 plus 9? 25. Eventually, you'll just remember that 4 squared plus 3 squared is 5 squared. It's what's known there's one known as a Pythagorean triple. Cool. So if h squared is 5 squared, then what is h? 5. Maybe I'll write plus or minus 5, but why is minus 5 not a reasonable answer? Yeah, it's a triangle.
Did you mean to write 5 squared and not cubed?
I did. Right, 25 is not 5 cubed. 25 is 5 squared. Yeah. So h is plus or minus 5, but in fact h is just plus 5. It's a triangle. I don't know what it means for a triangle to have a negative side length. Neat. So now that I know all 3 side lengths of the triangle, can I read off what the trig functions evaluated at this angle theta are, even though I don't necessarily know what theta is? What's the cosine of theta? 3/5. What's the sine of theta? 4/5. What's the tangent of theta? No, 4/3, right?
Yeah.
I guess the cotangent of theta would be 3/4. If you care about that. So we haven't talked much about computing trig functions. But one thing which you know for a fact is there are techniques to compute them because, for instance, your calculator is capable of evaluating trig functions. It'll give you decimal approximations, but if you want approximate answers, that's just fine. So let's use this to now do some applications. So here's one. Surveying. So you see occasionally surveyors doing things like measuring heights of buildings. They have like this doodad on a tripod where they look through an angle up. That thing, at the bare minimum, is what's called an avenue level. All it absolutely needs to have to function is a meter stick so it knows how high up it is, a thing to look through, a piece of string so that it remembers what down is, and then, well, I guess that's the job of the meter stick. The meter stick doesn't know what direction down, so you need the string to know. And then also a compass, not in the sense of something that always points north, but just something that will measure an angle of deviation. Because once you have that much, you can figure out the straight line from where you're standing to the top of the thing you're looking at. You can figure out the angle of elevation of that. And if you combine all those things together, you get what's known as an avenue level. So let's use an avenue level and do some computations. One thing which I think would be a neat exercise to do for the sake of this class would be to let you pick up an avenue level, a piece of string, pick up those doodads from my office, and then go and tell me what the height of Hippon is by making some measurements. I haven't yet gotten the wherewithal to assemble things together to do that. But you could. Let's. Sorry, I'm getting distracted. Let's do a computation given some known things. So a surveyor sets up an avenue level 100 meters from a building, which the surveyors measure by taking one of those wheelie things and walking out until it says 100 meters from the building. Computes the angle of deviation from horizontal from the point where he stands to the hinge loop, and that angle is 25 degrees above the horizontal. Sorry, I jumped out of my surveyor. They do all these things. Let's label some givens and figure out what the height of the building is. So what if this picture was supposed to be, well, there's like the height of the building. And here's the surveyor. Then what things in this triangle can you fill in?
The angle and then the length of them to the building horizontal.
Yeah, you can fill in the angle, and you can figure out the length from the surveyor to the base of the building. What is the angle of elevation? 25. And maybe I'll point out that it's in degrees, so when we do go and use a calculator to make our computations, we'll need to make sure we're walking in degrees. What is the length from the surveyor to the base of the building?
100 meters.
100 meters. And let's go ahead and assert that this building is actually built correctly, so it goes straight up. Is that enough information that you could solve, if you like, for the height of the building? What trig function seems useful? Tangent seems like it might be a handy one. So let's see, SOHCAHTOA. So tangent of 25 degrees, TOA, should be opposite the height, which is the thing that we want to know, over adjacent, 100 meters. Does that look like you could solve that for the height of the triangle? I bet. What would you need to do to that to solve it for height? Multiply both sides by 100, so you'll get height of this building is 100 meters times 25, nope, times the tangent of 25 degrees. Now, the tangent of 25 degrees isn't a number that you should just know, but it is a number you're capable of computing with a machine aid. Come on. No, wait, I think like Chrome has a machine. No, it seems fine. 100 times the tangent of 25 degrees. Somewhere around 46.63. What are the units? Meters. That application seem pretty reasonable? So trig functions are what you need to use if you want to convert from horizontal height to vertical height in any meaningful way. Let's do one additional one, and I think maybe I'll even give you guys some time to meditate on this. So, there is a building whose height you have measured by using this technique. You found the height of the building to be 100 meters. You stand back a distance. You don't bother measuring what distance you stand back. And take out your ID level and measure the angle of incline from where you're standing to the top of the building and find that that's 45 degrees. You then increase your angle of elevation, so you're looking at the top of the horse, and you find that this little angle is exactly 5 degrees. Do you think that this is enough information to determine the height of the horse? Should be. So here's what I'll suggest. I want you guys to do this, and go ahead and collaborate with those around you. If you don't see how to go straight to the desired quantity, I mean, of course you don't, because there's no obvious way to get from where you are to where you need to go. Just compute anything. Just find side links. As long as you just keep computing stuff, eventually you'll get to where you need to go. Yeah.
So
Yes, you will be in radian mode. And I can't tell you how to switch from radian mode to degree mode because I don't know. Yeah, cool. Alternatively, what you could do if you couldn't figure out how to do that is you know how to convolve in degrees and radians. So it would have been, I guess, 25 times
Well, you would do it like that, like
180 over pi.
I was thinking
And that would have done the job.
the rest of that, so I used like 50.
Now, 25 times pi would be
Well, that
180.
matter. We take 50 degrees tangent equals the question of so like this. Do R over 100.
So maybe just because of that, I think I asked this last time, but I'll ask it this time
Or
again.
that'd be different.
So you have these computing aids called calculators, but you need to be able to tell them whether you want to walk in degrees or radians.
Yeah, 100 though.
Does anyone not know how to change their calculator from degree mode to radian mode, or conversely? Okay. Even if your hand did go up, I wouldn't be able to tell you how because I mean, different calculators are like different. But I guess that's probably like a mode button on your front screen. That would be a good place to start. Alternately, any manual you ever want to find is available online, which is why they don't give you the calculator with the manual anymore. Just grab that PDF and do a quick find. Not right now. That one might be able to do radians. Nice. So I've given people some time to think about this. Do people want more time before we talk about it? Is there helpful more time? Okay, then let's go ahead and talk. And maybe I'll jump straight to the end. What is the height of the horse? Approximately say that louder.
19.18.
In meters? What was it exactly?
It was 150 minus 100.
100 tangent of 50 degrees. When I don't put any units, I'll assume that it's in radians, so I'll emphasize degrees. Minus 100, and maybe I'll put the units in. Even though I know that oftentimes I suppress units entirely. Nice. Shall we talk through where that answer came? Well, maybe I should ask first, did anyone get a differing answer? Okay. Let's talk through where that answer came from. And write it down. If you don't see how to finish a problem all at once, just try to do something. Eventually you'll figure out the right things you need. What's a quantity that you see that you can compute in this picture? You can see the adjacent side because you see this little right triangle, which is a right triangle, right? I assume my building stands straight up and down. This is not a top of the Leaning Tower of Pisa. So how can you figure out the length of the base of that right triangle? Yeah, you could use tangent. You could say, oh, well, I know it's a 45, 45, 90 triangle, so I know the base will be the same, but let's pretend you don't notice that. Let's call it B for base. So you know that the tangent of 45 degrees will be opposite over base. So base will be 100 times the tangent of 45 degrees. Tangent of 45 degrees is 1, which we will establish starting on the next page.
Yeah. Would be, so you'd have to multiply that B over and then divide by tangent of 45?
Yes, I guess it doesn't make a difference because it's 1, but yeah, that is what it ought to be. Thank you. Either way, that's 100 meters. Cool. But that's not the thing that I wanted to find. So how can you, what else can you figure out by looking at this picture? Yeah.
You could, you could add up the degrees and then do tangent again.
Yeah, so you can study this big right triangle where that big angle is now 45 plus 50 degrees, 45 plus 5 degrees, or 50 degrees. So this angle is 50 degrees. So you'll see that tangent of 50 degrees is opposite, which is the thing you want to know, plus 100 meters. Divided by adjacent, which is B, which you've already computed to be 100 meters. Does that look like you could solve that for a question mark? I guess you would multiply the 100 over to the other side, and then subtract that 100 over. Nice. That procedure seem pretty okay to everyone? So, in general, if you have questions that involve right triangles, you could address those questions by thinking about corresponding trig functions. And if you're trying to follow along by reading the book, this is maybe the first instance where I've gone drastically out of the order that the book presents things in. So this is coming from like chapter 5 and chapter 7 at this point, as is indicated on the webpage. And the homework will, as a consequence, come out of both chapters. So let's now go away for, so this has been a very applied set of examples. You could imagine that if the numbers were things you actually cared about, you could answer questions that you actually cared about as opposed to these made-up questions. Maybe you care about this. You care about the height of this fantasy horse atop this building, which probably doesn't exist. Let's try to go away from the applied and go towards the pure. So let's try to make computations for some explicit angles so that we'll be able to build, if you like, a lookup table for angles that you can plug into trig functions. And we have some angles already. So just by looking at this table, which of those angles do you just already know the trig functions of? Let's just try to read them out. If you start at 1, 0 and rotate by 0 degrees, then what point do you land on? 1, 0. So what's the cosine of 0? What's the sine of 0? What's the tangent of 0? What's another one of those angles that's an angle that you just already know what it is?
Pi over 2.
Pi over 2, because that's a right angle. So if you start at 1, 0 and rotate forward by a right angle, where do you land?
0,
0, 1. So cosine is 0, sine is 1, tangent is undefined.
And that's your 45.
Thank you. I should read before I write. So that'll be annoying because I don't use erasable things. So my notes will look ugly. I thought that we can figure out the remaining entities by thinking about right triangle trigonometry. And let's go ahead and do it. So, all right, so there's the picture that you need to fill in those first and last columns. But let's think about an angle of pi over 4. And let's do it by thinking about right triangle trigonometry. So here's a triangle. It's a right triangle. This base side is is angle pi over 2, which is a right angle. This angle is pi over 4. And let's just try to figure out the side lengths in this right triangle and decide what we can tell. Let's start by figuring out that angle alpha. What do the interior angles of a triangle have to add up to? 180 degrees, or how many radians? Pi. So, what did you say, pi? Sorry, I'm bad listening. I think you said what? Did you say 180?
Yeah, it's 180.
Okay. Yeah. Okay, so these things have to add up to 180 degrees or pi radians. So I know this angle, I know that angle, I don't know alpha, but I know what they add up to. Is that maybe an equation you could solve for alpha? I think so. Let's do it. So I guess pi over 4 plus pi over 2 plus alpha, which I would like to know, is equal to pi. So if you take that and you solve it for alpha, what do you get? Yeah, pi over 4. Pi over 4? No one actually wants me to go through the algebra, do they? Okay. All right, it's do some subtraction. And be careful with how fractions behave, I guess. So nice. This angle is pi over 4. And the thing to notice now, are two angles in this right triangle equal to each other? Yeah. These two angles are the exact same. The fancy one is this is an isosceles triangle. A triangle in which two opposite angles are the exact same is called an isosceles triangle. And an important thing about isosceles triangles is if those two opposite angles are the same, then the corresponding side lengths are the same. If you like, you could take that triangle and do a reflection to it, which would resolve all the side lengths, and you would throw the side length A exactly onto the side length B. Let's see, this is a right triangle. Could we apply Pythagoras' theorem to figure out what the side length C has to be? Yeah, C squared will be A squared plus B squared. Would you rather replace all the B's in this formula with A or all of the A's with B? Because right, they're the same. There's no need to have both symbols. Replace all the A's with B's. I think that's what you said. It doesn't matter which, right? It'll be the exact same. So let's replace all the A's with B's to see that that'll be B squared plus B squared, or 2B squared. So I see C squared is equal to 2B squared. Is that easy to solve that equation for C? What is C?
C over 2, or square root of 2.
Well, it would be like B times the square root of 2, right? And in fact, maybe it looks like it should be plus or minus, but again, this is the side length of a triangle, so it can't be negative. So C is equal to B times the square root of 2. Maybe you would want to write that as root 2 times B. If I write it that way, though, it's clear that the B is not inside of the square root. Everyone pretty happy with that? Nice. So now let's use SOHCAHTOA and see what we can see. So I'll redraw that picture. pi over 4 right angle b root 2. I guess. So let's, well, yeah, let's leave that a over b, because that was a, that was c. Of course, I just write garbage down. So, cosine, so it's SOHCAHTOA. So cosine should be the adjacent side divided by the hypotenuse. So it'll be what was originally the side length A divided by the side length C. But I know what A is. A is B. I know what C is. C is B root 2. So cosine of pi over 4 is B divided by B root 2. Does anything cancel in that?
B.
The B's cancel, so you're left with 1 over root 2. And on the one hand, like, there's an answer. But we should probably simplify that answer so there's not a square root in the denominator. What do you do to this to rationalize that denominator? Yeah, multiply and divide by root 2. And so what are you left with? Nice. So there's something. Now we can fill in an entry in this table. The cosine of pi over 4, the thing that I wrote in without thinking about what I was doing, is the square root of 2 divided by 2. Everyone feel pretty good? Similarly, do you think you could figure out what the sine of pi over 4 is? Yeah, what is it?
Root 2 over 2.
It's the same as we just had. Maybe that's, it would be polite of me to say, does anyone want me to talk through why that works out to be root 2 over 2? Okay, cool. Sine of pi over 4 is root 2 over 2. Tangent is opposite over adjacent. So by looking at that triangle, what is the tangent of pi over 4? And if you like, here's an aside in blue. So recall 45 degrees is the same thing as pi over 4 radians. So that also tells you the tangent of 45 degrees is 1, which is what we used in that previous computation. Everyone feel pretty good? Let's fill out the remaining ones. Let's determine the trig functions at pi over 3 and at pi over 6. We will do so by studying this triangle, which may be a word about notation. I will refer to a whole triangle by drawing a triangle and then writing the names of the vertices. So this triangle is denoted by triangle ABC. I will denote a line with its endpoints with a bar between them. So that line is AC with a line on top of it. And one other thing which I won't do right here is if I write a side length and put vertical bars around it looking like absolute value. That'll mean the length of that line segment. So that's just some notation, which is handy when you're talking about these things. So here's a triangle. Let's try to use this triangle to figure out the trig functions evaluated at pi over 6, because that's one of the things we want. It's on our list. So let's see. There's an angle of pi over 6. There's an angle of pi over 2. So do you think you can solve by looking at that blue triangle and figure out what alpha needs to be? What does alpha need to be?
5 or 6.
Nope.
Pi over 3. Alright, so by looking at the blue, just this shaded in blue triangle, you'll see pi over 6 plus pi over 2 plus alpha is equal to pi. So alpha is, I'm going to get everything in the common denominator, which I guess will be 6. So it'll be 6 pi over 6 minus pi over 6 minus 3 pi over 6. Let's see, 6 minus 1 is 5 minus 3 is 2. 2 pi over 6, also known as pi over 3. So this angle is pi over 3. Do. So that's studying the blue triangle. This triangle on the bottom is constructed by taking that blue triangle and exactly reflecting it over the line AC. So it's the exact same triangle again, where this is also a right angle. This angle is the same as that angle, so this is an angle of pi over 3. And let's see, that's like two right angles next to each other, so this is actually a straight line. So you put those two triangles together, you still have a triangle. So look at that big triangle. What can you tell me about the various angles of that big triangle? What's the size of that angle? That angle? This angle? Also pi over 3 because it's 2 pi over 6. So all of these angles are the same. They're all the same angle. So this is an equilateral triangle. So all side lengths are the same. That makes sense? So let's write that down as an equation. That tells us that this side length, A, is the same thing as this side length, 2C, is the same thing as this side length, A. One of those equalities is redundant, right? A is equal to A is not an interesting fact. But that's okay. Does that look like an equation that you could solve to see what C has to be? What is C? A over 2. So let's draw, I'm going to draw the little triangle, the blue triangle again. So I see that this is unknown, it's B. This is C, which I found to be A over 2. And this is A. Do you think one could use the Pythagorean identity to figure out what B is? I think so. All right, let's write down what we have. So the hypotenuse, A squared, must be B squared plus the other side length, A over 2 squared. So there are two things you don't know. You don't know A and you don't know B in that equation, but does it look like you can maybe solve that to figure out what B is? Sorry, I phrased that the wrong way. Solve that equation and tell me what B is. I think that's enough space. once you have it, tell me what you got.
B equals A over, or B equals A minus A by 2.
I think that you have made an error with your square roots. So let's go through and do it. Let's expand out that A over 2. What is A over 2 quantity squared? A squared over 4. So this piece is A squared over 4. So let's subtract A squared over 4 to the other side. So A squared minus A squared over 4 is equal to B squared. So what are you left with if you take A squared and subtract a quarter of A squared from it? Yeah, 3 quarters of A squared or 3A squared over 4, whichever you like. So what do you want to do now if you want to solve that for B? Take the square root of both sides. So you get B equals plus or minus big square root A squared times 3 over 4. Don't worry, I will do this. And let's take a look at that. Do you see any perfect squares under that square root? Yeah, I see a 4. I also see an A squared, which is a square. So you pull those two things out. I'll leave the plus or minus because I haven't said anything about it yet. A root 3 over 2. Can I throw out the negative choice?
Mm-hmm.
It's the side length of a triangle. So now let's do some computations. So the sine of pi over 6, sine is opposite over hypotenuse, so that will be c over a. But I know what c is. C is a over 2 over a is, what is a divided by 2 and then divide by a? It's just a half, right? If I take a, I divide it by 2, and then I divide it by a. That's a half. Cosine of pi over 6. Well, that will be cosine is adjacent over hypotenuse, so that'll be b over a. And I know what b is. B is root 3 over 2 times a. So I'll have root 3 over 2 times a, and then I divide by a. The a's cancel, leaving me with root 3 over 2 is the cosine of pi over 6. The tangent of pi over 6, tangent is opposite over adjacent. So that'll be a over 2 divided by a root 3 over 2. And maybe I'm going a little bit faster now. So that will be a's cancel. The 1/2s cancel. That's 1 over root 3, also known as root 3 over 3. And you'll notice that I haven't touched the pi over 3's yet. But do you see pi over 3 in that right triangle? So we can play the same SOHCAHTOA game. Sine of pi over 3 is opposite, which is b, divided by a. So SOHCAHTOA sine is b over a, which we have already computed. Is root 3 over 2. Similarly, what's the cosine of pi over 3? 1/2. What's the tangent of pi over 3? Just the square root of 3. That got fast at the end. People feel okay about that though? Nice. So, you'll notice that I didn't take the time to flip back to the previous page to put those entries in that table. You might want to do that if you want your notes to be complete, if you want to reference your notes. Yeah.
For those bonus problems in the homework this week, can we just turn those in any time, or are they due tomorrow?
In fact, I will ask you explicitly to not turn in the bonus problems tomorrow.
Okay.
Because I'll get confused. I'll have too many papers.
Okay. Just
I don't know.
to your office.
Let's say like, well, you can pawn them in class. Like I have a place to put them. But if I have two different things being pawned in, I'll get confused. So I'm going to go ahead and say this. I'm announcing this on the spot right now. The bonus homework problems, let's put a deadline on them. Let's say Friday of this week. Yeah. Yeah, so the bonus problems that we just asked about, there's a set of problems on the homework which I didn't cover the supporting material. It's recorded as a video now, but they're labeled as bonus problems when they come to website. So you're going to get this equation. That's good. You just need to solve that equation. No, I suppose.
Jesus Christ. Don't do that to me.
LN of 5019. Well, that should be like equals to, I just looked up equals. Is this supposed to be 1,000? And that's 10,000?
Which one? Fine.
And that was 10. That would be LN of 10.
I love sleeping in
That even times in the box space. That's 9 things.
Oh yeah. Yeah. I try too. So I hate going like I'm dressed like this.
So?
There was a time where
Today's Tuesday, right?
Yeah.
Yeah, 1 to 2. ln of 10 times 5 over 9.
So gorgeous.
You say it should be somewhere around 1.2? And that's supposed to be a 9 over 5?
This, I don't know, this one was like really good. Was that? Really good, yeah. Like, I thought it was like being played from his
So here's what you should do to make a sanity check. You have a t-value. It is whatever it is. Plug in that t-value. And see if you actually get that right. And then you carefully read the problem and see if everything is as you say it should be. So the book says, for example, that it should be, that the answer is like 3.9. Plug in 3.9. See what that is.
I always run upstairs. Like, if there's no one in front of me, I will look
Population
it
B in
upstairs.
47 days. So that's telling you
When I do it,
what time is
I
right.
walk upstairs.
So that's just plug in P equals 47 days.
I have to go over everything.
No, I got
No, I usually go down a set of stairs.
The phone's still up.
Oh, yeah.
I walk up the stairs though because I can get it. I get lost. And I'm like, you know what, I should have taken the
This is all 42? This is 42. Use the formula that you got in part A. You have the formula. Does it have a T?
to convince them to go on like a exercise class.
I am. This was I knew it was going to get me through campus, but
I'm
like,
like, I'll try, but I'm not gonna have much luck.
Yeah, so this models the population.
I've been begging him.
yeah, I'll dress it later so I don't die over there. Mistake.
Last story is that,
But it's like 85. Also, I started.
I got my driver's.
I have one reason I'm not. Tons of reasons. I don't know where this is going. That's the last Halloween party. It's like, I have to.
literally, yeah, Sam's like, yeah, I went to a party. With ours. Saturday. Yeah, Saturday. And I was like, oh yeah?
Yeah, same. I'm not supposed to
And
back
I'm like, yeah. I'm like, what did you do? I'm just kidding. Because I went to go and also the original. And I'm like, I knew it. I was like, see, I know it's not. And then I was like, that's why I don't trust you because you have literally everything that either wears neon yellow or orange. So I'm like, well, how hard can it be to get him to wear orange t-shirt?
Oh, it's still recording.
But then he's like, I'm not wearing this. And I'm like,